we've talked about the 0 over 0 type of limits. But I suppose I should say, before you even do that, thank you so much. The first thing you want to do is plug it in. If you're trying to evaluate a limit and you can just substitute in what x is equal to, that's usually a great start. And this looks a little off kilter. Here we go. Okay. So for example, the limit as x approaches 3 of 2x squared plus 5 over x plus 1. You can just substitute in 3 there, and that's going to be the limit. That's going to be 2 times 3 squared plus 5 over 3 plus 1, which is something. What? 18 plus 5, 23 over 4. And then we have 0 over 0 type of limits. And there's really kind of, I would say there's 3 or 4 things we generally see with the 0 over 0 type. We see either using factoring and canceling. For example, the limit as x approaches 5 of x squared. Let me think for a second, make sure you're right. Yep. Sorry, now I'm like, let me see here. Minus 6x plus 5 over x squared minus 25. It's a great example of having to factor and cancel. You would factor out the top, right? Well, I should say it's a great example of the 0 over 0 limit. If you plug in 5, you do get 0 on top and 0 on the bottom. And the way you would deal with this would be to factor the top is x minus 5 times x minus 1. And the bottom is x minus 5 times x plus 5. And this x minus 5 to cancel. And then you plug in 5 for the remaining x's, and you get 5 minus 1 for 5 plus 5. Or you might have to, multiply by a conjugate. For example, the limit as x approaches 6 of the square root of 2x plus 4 minus 4 all over x minus 6. Here we would definitely multiply the top and bottom by the conjugate of the square rooty thing. So square root of 2x plus 4 plus 4 over the square root of 2x plus 4. I guess we might as well do the work since we're already showing the things. So this ended up being the limit as x approaches 6. This is not what we wanted. When you multiply conjugates, you get the first thing squared minus the second thing squared. The middle terms cancel. That's the whole reason for multiplying by the conjugates. And the bottom, you just get terrible stuff. You don't multiply it. You get x minus 6 times the conjugate. And then we simplify. We usually end up doing some factoring and canceling. The numerator is 2x minus 12, which factors as 2 times x minus 6. And then you can cancel the x minus 6 in the numerator with the x minus 6 in the denominator. And you end up getting 2 divided by the square root of 16 plus 4, which is 2 over 8, which is 1/4. Oh, thank you. Appreciate it. And then the last kind of typical algebraic 0 over 0 type of limit is where we have to do some common denominator action. So these are the 3 sorts of algebra we usually do when we have a 0 over 0 type of limit. We either try and factor and cancel, or if that's not an option, we see a square root, we try and multiply by a conjugate, or if that's not an option, we see some fractions and fractions like the limit as x approaches. Let's make it not too terrible. 6 of 2/3 minus 4 over x all over x minus 6 again. Sure. I don't really want to do it, but I will. You get a common denominator, so you multiply this 2/3 by x over x and this 4 over x by 2 over 2, or sorry, 3 over 3. Actually, you know what I do first? I check to make sure that I needed to do this. I would actually plug in 6 and see, oh yeah, I do get 0 over 0. I get 2/3 minus 4 6, which is 0, and I get 6 minus 6, which is 0. So it's always good to check that you actually need to do something like this before you start doing it. Here we're going to get the limit as x approaches 6 of 2x minus 12 over 3x all over x minus 6. Getting a little messy there. Oh, I forgot to put my face on the screen. Not that it's super important, but I feel like it's weird when the video doesn't have me. So let me go ahead and add my face in there if you guys don't mind. Maybe. Sure. I'm going to cover up the answers if there's one. I don't know if you guys disagree. If you think the video is fine without my face, I don't have to put it in there, but it feels weird to me. So anyway, there we go. And then simplifying this, we get the limit as x approaches 6 of 2 times x minus 6. Sorry, it's a 6, believe it or not, over 3x times 1 over x minus 6. And the x minus 6 is canceled. And we get 2 over 3 times 6, which is 1 over 9. So these are the kind of standard 0 over 0 type of limits that you'll see. Where you have to do some sort of algebra to make it work out. Not the only kind, though. And we briefly started talking about it last class, I think. Yeah, I think we did. Looking at my notes, which yeah, we definitely last time, but I want to say it again because it is important. Last time we talked about the limit, at least remind me, we talked about this limit, I think. Yes, we did. Limit x goes to 0 sine x over x. We started talking about it. So this limit is 1. And I think we talked about how you can see it graphically last time. I just want to show you all again because it is a nice graph to think about in your head. There's the graph of sine of x over x. And you can hopefully see that as the x values get closer and closer to 0, the y values get closer and closer and closer and closer to 1. That's the idea, right? So limit as x goes to 0 from either side of sine of x over x is equal to 1. And I think I even went a little further on about this. I said something to the effect of, I can just do this. I can be smart. Can I be smart? I can be smart. All right. I said that it doesn't really matter what you've got as long as the idea really here is that if you have the limit as some stuff goes to 0 of sine of stuff over the same exact stuff, this limit's 1. As long as these things have to be exactly the same and going to 0. And I think I made up some example like the limit as x approaches 4 of sine of 3x minus 12 over 3x minus 12. That limit is definitely 1 because it meets all the same criteria. The stuff is the same, right? You have sine of some stuff divided by the same exact stuff. And the stuff is approaching 0. Now, I know the limit says x is going to 4, but if x is going to 4, then 3x minus 12 is going to 0. So the stuff is going to 0. And might as well take a look at it. We can look at the graph of this too. It's kind of neat. In fact, let me just do that. Let's just change that one up. Okay, we got a 3x minus 12. And the bottom, same thing. And if we look over at 4, oh yeah, look. As x gets closer and closer to 4, the y values definitely get closer and closer and closer to 1. So really, really is true that as long as the argument of the sine function and the denominator of that expression are the same and both getting closer to 0, well, they have to both be if one of them is, then the limit's going to be 1. And then, of course, It's not going to be 1 necessarily if the stuff isn't getting closer and closer to 0. For example, I've definitely seen people say something like the limit as x goes to 5 of sine x over x. That's not equal to 1. This is an example of just plug it in. It's not going to be a very well-known number. I don't know what sine of 5 is, but it's a real number. That's your answer. You can get the decimal approximation. Nobody wants you to get a decimal approximation. They want you to leave it like this. Let's see, I feel like there's something else I want to say here before I get too into this. No, I think we're good. Yeah, so the question becomes, without using L'Hopital's rule, L'Hopital's rule is not on the, so if you've never heard of L'Hopital's rule, great. You're not allowed to use it anyway right now. If you have heard of it, it's not on the table currently. You can't just use L'Hopital's rule right now. And then you might want to, but you can't. So if I want to find the limit, as x goes to say 0 of sine of 6x over x. Oh, sorry, you can't see that. So I kind of have half of the stuff I need. Like I have sine of something and another something, and both those somethings are going to 0, but they're not the same. And there's a number of ways of dealing with this. I have found the easiest way of dealing with this is what I like to call the wish method. I'm going to rewrite my fraction as 2 fractions. I'm going to write it as sine of 6x divided by something times something divided by x. And currently, I haven't changed anything. Still the same old thing as it ever was. What do I wish was in the denominator of my sine of 6x fraction? I wish there was a 6x there, right? So with sine of 6x over 6x, its limit would be 0. Okay, well, wishes come true. There we go. But we have to accommodate for that, right? You can't just divide by 6x without changing anything else. We also have to multiply by 6x. Is it the same as it was before? Yeah, it's the same, right? I didn't change anything. I mean, I did change something. I multiplied and divided by 6x, but really all I did was multiply by 1. It's still the same expression as it was before. But now it's more manageable because I can cancel this x here with that x there. And these x's definitely cancel out. And so now, if you really want to, I don't think you need to do this. So here's what I would really do if I was finishing this problem. I would say that this is equal to 1 times 6. And I would actually write 1 times 6. I wouldn't just jump straight to 6. I think showing that step shows that you know that the limit of this part here is 1. It's going to multiply by 6. But I will point out, here's what someone else, maybe your teacher might want you to do instead. Another option, we say, okay, this is equal to the limit as x goes to 0 of sine of 6x divided by 6x times 6. And then there is a rule for limits. It says if you have a limit of a constant times a function, that constant multiple can multiply the entire limit, meaning I can rewrite this as the constant 6 times the limit as x goes to 0 of sine of 6x over 6x. Do I think this is necessary? No. Might someone ask you to do this anyway? Possibly. So I would say, okay, I've got that. And then that's 6 times 1, which is 6. But yeah.
So is this only when you're working with sine, the rule where if the bottom and top are the same, it'll equal 1?
I would, so I'm going to say yes to that, but I'm going to rephrase it slightly. When it's the argument of the sine function, right? Not just the top, but the sine of the stuff and the bottom are the same. It's not that it's equal to 1, it's that the limit is 1. But yeah, but yes, you've got the right idea.
Okay, but that only happens when you're working with sine.
Right, in contrast to
like tangent or
well, tangent's the one exception to your statement. But yes, we're going to talk about tangents.
Okay.
But to address your question, or I think to address your question, if someone asked like, what's the limit as x goes to 0 of say cosine of x over x? Definitely not 1. In fact, this is something we're going to address today as well. This limit is, I think it doesn't exist actually, because it's a two-sided limit, but I feel like we're going to come back to this. I want to explore this a bit more first, but we'll definitely get there. Don't worry. So we're coming back to that. All right, so I want to do a few more of these sine ones because they do come up. So let's say we want to find the limit as x approaches 0 of, say, sine of 5x over 3x. So people do this different ways. I personally like the way I do it because that's the way I've done it. But some people would take this and multiply the top and bottom by 5/3. That's also a perfectly legit way of doing it. So another way to attack this, we say, oh, I know I want to get a 5 in the denominator, and 5/3 times 3 is 5. So you can say this is the limit of, as x goes to 0, of 5/3 times sine of 5x over 5/3 times 3x. But really, you're still having to answer the question, what do I want in the denominator? Right? That's what we're always thinking of. What do I want in the place that sine isn't? I want the same thing that's in the sine function, as long as it's going to 0, which it is. So we could say, oh, that's the limit as x goes to 0 of 5/3 times sine of 5x over 5x. And then the 5/3 can come out. And then we get 5/3 times 1. Because again, this thing here is meeting the criteria. 5x and 5x are the same, and they're both going to 0. So the limit of that is 1. I should really stress sine of 5x divided by 5x does not equal 1. Ever, actually. But specifically, we're not saying that this is equal to 1. We're saying that as x gets close to 0, this expression gets closer and closer and closer to 1. Yeah.
So does this like method that the wish method I use, does it only work when it's a sine limit going to 0?
Typically, yes. I'm not, but as opposed to what?
Like say if it was like tangent.
Well, no, it works for tangent too. No, well, it doesn't work for cosine because, so the thing is, basically sine and tangent are the ones that kind of have this quality. And it's actually kind of interesting if you really think about what we're saying here. What you're actually saying, let me go back. Sure. Let me right here for a second. What you're actually saying when you're talking about this, the limit, I'm going to use theta for a second. As theta goes to 0, of sine of theta over theta. What you're basically saying is the ratio between sine of an angle and the angle, they essentially become kind of equal to each other as that angle gets really small. And this kind of goes back to trigonometry, really. So if you think about how we define sine in a circle, so if this angle is theta, what that really means is if your circle has an arc length of 1, which we're typically thinking of when you're doing trigonometry, it's the, sorry, not an arc length, a radius, I apologize. Your circle has a radius of 1, then this arc length here is equal to r times theta, which is r times, sorry, which is 1 times theta, apologies. That length is theta, and if you drop a perpendicular, how do you find sine in the right triangle? It's which over which? Right, so it's this length here divided by 1. So this length here, which I'm just going to say is, we call that A and not B. The sine of theta is the length AB. Now, I would like to imagine, sorry, I'd like to imagine you could see the picture. I'd like to imagine that you guys might agree with me that this length here and this length here are pretty close to each other. And that as this angle gets smaller and smaller and smaller, those lengths get closer and closer to being equal to each other. It's true. And it's true. And this limit is that is actually saying that. That's what that's all the words are falling on my mouth in the wrong way. That's all that limit is trying to say. Is that, oh yeah, this value sine of theta, which is this length here, and this value theta, which is that length there, as the angle gets smaller, those two lengths become closer and closer to each other. Kind of neat. It's another way of viewing it. Do you need to know that for real? Probably not, but it's good to know things, the background of things, even if you don't actually have to know them for later on. Again, if I were doing this limit, I would have done it as the limit as x goes to 0 of sine of 5x times something over 3x. And then I would have said, oh yeah, I would love for there to be a 5x there and a 5x there. And then cancel the x's. And then said, oh yeah, it's going to be 1 times 5/3. And you really have to emphasize strongly, I'm not saying sine of 5x over 5x equals 1. I'm saying the limit as x goes to 0 of sine of 5x over 5x equals 1. And then the 5/3 is just the 5/3. They do get slightly more complicated. Like if you have the limit as x goes to 0 of, sure, sine of, oh, this will be interesting, sine of 7x over 3x, sorry, sine of 3x. Now, something you'll start to notice for a lot of these is you often get the fraction that's the quotient of the coefficients of x. Like in this one, we got 5/3, and the previous one, we got 6/1. Here we are going to get 7/3 as our answer. We still need to show the work. So, I'm going to keep track of time too. Have a sine of 7x. There's no good way, unfortunately, of bringing that sine of 3x up to the top. So we're just kind of stuck with it being in the bottom. What do I wish was beneath my sine of 7x? 7x. Need one in the numerator to balance it out. All right, so here's a slightly harder question because we haven't really talked about it. What do I wish was been above my sine of 3x? I do. Now, why? Well, it is also true that the limit as x goes to 0 of x over sine of x is also 1. Let me show you why. Because we can rewrite it as the limit as x goes to 0 of 1 over the reciprocal, which is sine x over x. But then, what's the limit of this part here in red? This thing, right? It's sine x over x, and we know its limit as x goes to 0 is 1. You can also use your limit rules to say the limit of a quotient is the quotient of the limits. So it's the limit as x goes to 0 of 1 over the limit as x goes to 0 of sine x over x. The limit of a constant is the constant. The limit of as x goes to 0 of sine x over x is 1. So if you have sine of x over x or x over sine of x, its limit is 1. Or more generally, if you have sine of stuff over some stuff, or the stuff over sine of the stuff, as long as the stuff is going to 0, that limit's going to be 1. So we really do, in fact, want a 3x up there. And then I would just say my answer is 1 times 7/3. Okay. Let's do a couple more. Let's talk about tangents. So how about the limit as x goes to, it's almost always 0 for these sine and tangent ones, of tangent of 12x over 2x. So tangent's special, but it's not, you don't really have to be that, you have to know one thing about tangent. The tangent of x is equal to sine of x divided by cosine of x. So I'm going to rewrite tangent of 12x as sine of 12x divided by cosine of 12x. And this feels like a terrible way to write it. I should probably have really written it like this. Limit as x goes to 0 of sine of 12x divided by cosine of 12x times 2x. And here's what I'm going to tell you. It doesn't just disappear, but as far as we're concerned, we can really just kind of not pay attention at all to cosine. It's not going to worry us. It's not going to bother us because what's cosine of 0? It's this many. Sine of 0 is 0. Cosine of 0 is 1. So when we try to evaluate this limit, cosine of 0 being 1 isn't going to really make it any harder to figure out what's going on. I'm still going to do the same thing I did before. I'm going to wish. I'm going to put sine of 12x over something. And I can probably put everything else over there. I might not. I might separate this into multiple fractions just because that's kind of my style. And as usual, I want beneath the sine of 12x a 12x. And I'm going to put one in the numerator to balance it out. And I'm going to put it over the 2x. And then I don't need to do any more adjusting, right? You don't need to worry about the cosine thing here. So we just need a 1 in the numerator because there should be something there. All right, cancel some x's. So, oops, I don't need to write the limit anymore because I'm going to take the limit. Sorry. If you're getting a value, an actual number as your answer, you shouldn't be writing the limit as x goes to anything anymore. So as x goes to 0, sine of 12x over 12x approaches 1. And we're going to get 1 over cosine of 0. And we're going to get 12 over 2. The cosine of 0 is 1. So it's okay that it's in the denominator there. So I'm really just getting 1 times 1 times 6, which is 6. So tangent also has the same sort of rule. In fact, sometimes people write the rule, although I don't think it's really necessary to write it down, but the limit as x goes to 0 of tangent of x divided by x is also 1. But really, I would just encourage you to be like, oh, well, I know that's 1 because I know that it's really the limit as x goes to 0 of sine of x over x times cosine of x, which is really the limit as x goes to 0 of sine of x over x times 1 over cosine of x. And this goes to 1, and this also goes to 1. So I wouldn't encourage you to memorize this, although you certainly could. I would definitely encourage you to memorize the fact that the limit as x goes to 0 of sine of x over x is equal to 1, because that comes up fairly quickly. All right, let's look at one more, and then we'll move on to some other things. Limit as x goes to 0 of, sure, sine squared of 8x over, sure, 4x squared. So a word of warning here. Whoops. So far, basically every other limit we've seen like this, you've gotten the fraction of the coefficients, right? The previous one we just did, 12 over 2, ended up giving us 6, right? It's not going to be the case here when you have multiple instances of sine. Because really the way I'm viewing this is sine, well, limit as x goes to 0 of sine of 8x times sine of 8x divided by 4x squared. We're not going to get 8 over 4 as our answer. Because I don't just need 1 8 in the denominator to make this work. I need an 8x here, which is balanced out by an 8x there. And I need an 8x here, which is balanced out by another 8x there. And then, if we simplify things, the x's cancel. And I'm left with the limit of that's 1, the limit of that's 1, and that is the constant 8 times 8 divided by 4, which is just 8 times 2, which is 16. Or 64 divided by 4. So that's usually how people make these x approaching 0 sine x over x limits work, by doing this kind of stuff. Well, maybe not exactly. Someone might be doing something slightly different. Okay. So let's go. Where'd you go? I wanted to work my way back around to that cosine limit. So let's go ahead and look at something that's not that at all. Make the limit as x approaches 0 from the right. Sorry, not 0 from the right. Let's make it 6 from the right. Sure, let's go 3x minus 20 over x minus 6. I don't think we've talked about this type of limit yet in this class, although I could be forgetting that we did, because I know I did it in another class. So, but I don't think we have, so we'll do it now. So this is not a 0 over 0 type of limit. Right, if I plug in 6, I do get 0 in the denominator, but not in the numerator. I get 18 minus 20, which is -2. I do want to kind of emphasize here, when I'm approaching 6 from the right, I'm not really picking a number that's like a little bit larger than 6, right? I'm not saying let's plug in 7. I'm really saying let's just plug in 6 and then think about where things are. And so what I want to kind of mention here is that this number 0 here, this is not really 0. Because x isn't really equal to 6. X is just really close to 6. Now, in this particular case, the value of x is a little bit larger than 6, because we're approaching 6 from the right. X is a tiny bit, which would make the denominator slightly positive or slightly negative. Good question, James. X is let's pick a number. Let's make x very, very close to 6. Let's say that x was equal to like 6 plus 1/1000. Because we're definitely on the right side of 6 there. And so if we do that, well, I'm not going to worry about the numerator, right? I'm going to say that on top, we're going to get, all right, 3 times 6 plus, I don't really care, minus 20. But in the numerator, the denominator, I definitely care. Oh, sorry, thank you. And so we're going to get approximately, so the numerator, I'm just going to say is -2. I don't need to say that it's -2 plus 3/1000. Okay, fine, I could. It's not that hard. Except it's plus, and I did minus. That's what it would really be. But what's the denominator? Well, 6 plus 1/1000 minus 6 is going to be 1/1000. And when you divide by 1/1000, that's like multiplying by 1,000. This is going to be -1.997 times 1,000. This is going to be -1,997, which is essentially -2,000. Or as I'm sure someone has said to you before, if the denominator is really, really small, the overall fraction is very large. Right? We could have made this 6 plus 1/1,000,000th, and then we would be multiplying by 1,000,000 here. So we can see that as x approaches 6 from the right, this entire expression gets very negatively large. Or the way we would write this more standardly is the limit as x approaches 6 from the right of 3x minus 20 over x minus 6 is -infinity. And here's how this usually works. if we have a limit and we plug it in, sorry, let me write this down. If we get a 0 in the denominator and a non-zero number in the numerator, we know our answer is going to be one of three things. It's either going to be minus infinity, or it's going to be positive infinity, or it's going to not exist if the left hand and the right hand side are doing opposite infinity things. If it's a one-sided limit, it's always going to be one of those two things. One-sided limits are always going to be either positive, for this type of thing, are either going to be positive infinity or negative infinity. So we could also ask, what's the limit as x approaches 6 from the left of 3x minus 20 over x minus 6? And now here's what I usually write for a limit like this. I would say, okay, well, I know if I plug in 6 to the top, I'm going to get negative 2. I know if I plug in 6 to the bottom, I'm going to get 0. But then I'm going to think further, okay, is my 0 in the denominator, really, I know it's not 0. I know it's a very, very small number. It's close, oh, excuse me, it's close to 0. Is it slightly negative or slightly positive? Well, is x a little bigger than 6 or a little less than 6? A little less than 6, right? We're left of 6, which means we're less than 6. And if x is less than 6, then x minus 6 is a little bit negative, right? It's like 5.9 minus 6. Oh, it's a little negative. So the way I write that usually is a 0 with a minus sign for a superscript, to say that, oh, it's a little left of 0. It's a little less than 0. And in the previous one, I would have written that as negative 2 over 0 with a little positive superscript. That's just for me to know what's going on. If I know the answer is either positive infinity or negative infinity, I just have to think about what my signs are. I have a negative divided by a negative. Oh, that's positive. Done. That's it. That's all you got to do. Sometimes I've seen people when they do this, they kind of write this part in quotes, because writing something divided by 0 is a little iffy. But that's kind of it. There's not a lot else to be done there. You can write a bunch of words like I did for the previous one about x is getting closer to 6, and the denominator is really small, the whole thing's really big, but this is kind of the work we do for this. I should also point out that if we asked what's the limit as x approaches 6 of this expression, we would say that limit doesn't exist, because the left-hand side is going to positive infinity and the right-hand side is going to negative infinity. And this corresponds to there being a vertical asymptote of 6, right? When the limit as x approaches a real number is infinite or negative infinite, we have a vertical asymptote. And now if I know exactly what this function looks like, that's not true. I have a pretty good idea what this function looks like. I know that at x equal to 6, as we approach 6 from the left, it goes to positive infinity. As we approach 6 from the right, it goes to negative infinity. So it looks something like that. Question?
So we're only caring about what's happened under in the denominator?
Essentially, yeah. So I mean, when you're talking about a vertical asymptote, I think that's what your question is.
Yeah.
Okay. Yeah. So, but really, I'm just trying to address if you have a limit where the denominator ends up being 0 when you plug it in, and the numerator is not 0, then we know we have some sort of infinite limit. So if we get a non-zero number over 0 when we plug it in, we either get infinity, negative infinity, or it possibly does not exist for a two-sided limit. And those are the only options, right? When you plug it in, you get non-zero over 0. These are your three choices: infinity, negative infinity, or does not exist. Let's look at one or two. Time is always so fleeting. Let's say we want to look at the limit as x goes to 3 of 2x minus 5 over x minus 3 to the 4th. And you would like to see that problem, I would assume. Okay, so let's see here. I'm just going to plug in 3. Well, I'm not, that's not true. I'm going to look at both sides first, right? So if I just plug in 3, it's not helpful. So I'm going to look at the left. The limit as x approaches 3 from the left of 2x minus 5 over x minus 3. Now, here's where it's really important for the numerator that you really do plug in 3. Because if you said, I'm going to pick a number smaller than 3, and you pick 2, you get the wrong sign. And when you plug in 3 to the top, 3 times 2 is 6 minus 5 is 1. If you plugged in something like 2 on the top, 2 times 2 is 4 minus 5 is negative 1. That's going to completely change your entire answer. So when I plug this in this 3, I'm getting 1 on top. When I plug in 3 on the bottom, I'm getting 3 minus 3, which is 0. But it's slightly negative. Well, it's slightly negative before I raise it to the 4th power. Then it's going to be slightly positive because it's multiplied by itself an even number of times. So is this limit going to be positive infinity or negative infinity? Positive, right? Because it's a positive over a positive. So this limit, as x approaches 3 from the left, 2x minus 5 over x minus 3 to the 4th is equal to infinity. Great. How about the limit as x approaches 3 from the right? Well, again, I'm going to get the same sort of thing. I'm going to get 1 on top. I'm going to get a slightly positive 0 to the 4th power. That's just going to be a slightly positive 0. So here, what do we get? Also infinity. So what's the overall limit from both sides? Does it exist, or I should say, that's the wrong question to ask. What's the overall limit for both sides? It is positive infinity. Now, I did say something, and I feel like I should address it. Does that limit exist? No. We say it's infinity, but does the function ever, right? It's not getting closer and closer to infinity. You can't. It's way the heck out there. We're just saying that the function is getting larger and larger and larger without bound. But I really want to point out, it's not really that important, actually. No one's really going to get too caught up in this detail, probably. But if the limit's infinity, the limit actually doesn't exist. We say it's infinity because we're being more specific about the way it does not exist, but it still means it doesn't exist because the limit's not a real number. Real numbers are like 6 or the square root of 2 or 5/7 or pi, but not infinity. Ooh, nice. I know it's a terrible habit. It's not that terrible. It's not like I'm smoking cigarettes or anything. Right? There's lots of worse habits than doing that. Okay. How much time? Okay, so I did say I would attack this limit. Limit as x goes to 0 of cosine of x over x. I'm pretty sure it doesn't exist, but let's make sure that is true. So let's look at things from the left side. Let's go from the right side to 0, first of all. Okay, if you're on the right side of 0, well, we know the denominator is positive. Oh, we're not, this one's not. I'm trying to make this harder than it is. What's cosine of 0? 1. 1 positive over 0 positive is positive infinity. What if we approach 0 from the left-hand side? What's going to happen if we approach 0 from the left-hand side? Well, we're still going to get 1 on top, but now the denominator is going to be a little bit negative. So we're going to get negative infinity. So this limit doesn't exist in the way that one side's shooting up to infinity and one side's shooting down to negative infinity. So basically, when you're getting these limits that end up being infinity or minus infinity or doesn't exist, one of 3 things is happening. And I said this already, but slightly differently. If they're both going to infinity, you have a vertical asymptote like that. If they're both going to negative infinity, you have a vertical asymptote like that. And if one's going one way and one's going the other way, you have a vertical asymptote like this or like this. This one would look like I mean, not exactly like this, right? It's not how cosine of x over x exactly looks. I'm just giving you a very basic idea. But oops, come on, James. I hate that I have to like look for the, okay, there we go. Oh, I don't want a T there. What's going on? One of these times, maybe. Sure. There we go. Whereas something like 1 over x minus 1 squared has, oops, right, has both sides going up the same way. Both limits are going to positive. And then you could do something like the negative of that. To see, oh yeah, they're both going down to minus infinity. So that's what's happening. You've got limits that end up being infinity or negative. You're seeing where the vertical asymptotes are. And the vertical asymptotes are where x is, the thing x is approaching. So this one has a vertical asymptote at -2 because the limit as x approaches -2 on either side of negative infinity. And this other one, right, this green one, where's the mouse? Has a vertical asymptote at x equal to 1 because the limit as x approaches 1 from either side is positive infinity. It's getting larger and larger and larger and larger, and you can't stop it. I mean, you can obviously get off the screen, but yeah, it's very big. All right. Oh, it's 2:58. I could say more things. The last thing I was hoping to get to, but we don't really have a whole lot of time for, but I'll give you one quick example, is Squeeze Theorem. Squeeze Theorem, and really I know I have like a minute and a half. So let's just do a quick example. Let's say I wanted to show, or prove, however you want to phrase it, that the limit as x goes to infinity of cosine of x over x is equal to 0. Right, this isn't the limit as x goes to 0 of cosine x over x. We know that limit doesn't exist. But this limit is 0. And the way you would show it is the following way. And here's the way you show a lot of limits to infinity involving sine or cosine are what they are by using the squeeze theorem. And we're often going to use this important fact about cosine or sine. Between what two numbers? Right. The same is also true for sine. Sine of anything is between 1 and -1. It doesn't have to be just x. It can be sine of anything. -1. And then you try and make the thing that's in the middle look like the thing you want to take the limit of. So we divide everything by x in this particular example. And then finally, well, not finally, then we take the limit of the outer parts and we hope that they end up being the same. If they're not the same, you have to do something else. You take the limit as x goes to infinity of 1 over x, you definitely get 0. And you take the limit as x goes to infinity of -1 over x, you also get 0. Because the denominator is getting very large, the fraction is getting very small. And then since the limit of this is 0 and the limit of this is 0, this is stuck between them. So we can say by the squeeze theorem, and I honestly can't remember. Have we talked about the squeeze theorem in here before?
Yeah.
We have, okay. I was like, so I wanted to make sure you saw it. So here's one more example. Oh, yeah, I wanted to make sure you saw it, but not actually saw it. By the squeeze theorem, we get to say that the limit as x goes to infinity of cosine of x over x is in fact equal to 0. It's stuck between those other two things. And it is 3, but here's a nice visual of that. Yeah. So if we look at you can see, oh yeah, the cosine x function, if you scroll, you're going out, it's kind of lame. if we scroll further to the right, you can see, oh, look, it's always between those other two functions, and they're getting closer and closer to 0. So cosine of x over x has to get squeezed into 0 as well. I really like the graphing for the seam, the squeeze, like the graphing with the squeeze and stuff is like, oh yeah, it seems super clear, right? Obviously, if these two things get close to 0, you're bouncing back and forth between it. There's nowhere else to go. All right, you're free to go.